Good morning, everyone. Welcome to the seminar of the Social Sciences Division. It is with great pleasure to introduce to you our speaker, who is a development economist and a postdoctoral fellow of this division. Our speaker loves numbers, but he also has a big heart for helping the poor and the unfortunate. He was in New York during the 9/11 tragedy, and he volunteered in cooking and serving food both to the victims and rescuers on site. In New York, he pursued a master's degree in applied physics, which was also his bachelor's degree. And then he went on to work as a management consultant for business companies on marketing their products competitively. And these products include food, coffee, electronics, retail banking, but take note, beauty products. Until he realized that he was helping to make the rich get richer. But that was not really what his heart desired. He wanted to help people, perhaps through his research for development work. And so he went back to Japan and took a master's in international development studies and PhD in development economics at the National Graduate Institute for Policy Studies, or GRIPS, not GRIS, in Tokyo. This morning, he's going to talk to us about changes in the agro-climate effects on cereal crop yields, panel evidence from India, with implications for Sub-Saharan Africa. And this is a major portion of his dissertation. Ladies and gentlemen, please join me to welcome Dr. Takuji Tsusaka.
Thank you very much, Flora, for making a splendid introduction of me. And thank you all very much for taking the time to attend this seminar. And today, I will present my study on climate effects on cereal crop yields, particularly focusing on the changes of those impacts over time. And I have to mention that it's not a climate change study, but the focus is on climate endowment, the regional difference in climate.
It's on. It's already on.
It's already on. Okay. So I talk mostly about the changes in the impacts of climate, not the changes in climate. Anyway, let me start with the introduction. As many of you here are already familiar, agricultural production has improved dramatically in Asia, particularly in Southeast Asia, but also in South Asia, which is called the Green Revolution. Which is called the Green Revolution. And there are some factors behind it, but the most important of all is high-yielding crop varieties were developed and introduced, especially for rice and wheat. And the important support was the diffusion of water management, such as irrigation and tube wells. And another important support is the intensive use of chemical fertilizers. And there are also other factors, such as markets, infrastructure, credit, education. For example, if road condition is better, it reduces the transportation cost. So for farmers, the output prices go up, and the prices of essential inputs like fertilizers can reduce. However, in Sub-Saharan Africa, agricultural production growth has been so stagnant. The cereal yields have been slowly increasing in Sub-Saharan Africa, but the rate of increase is not so high compared with other regions. As a consequence, the rate of increase has been outstripped by its population growth rate, and per capita cereal production has been this stagnant. Now, why has SSA missed the Green Revolution? I just mentioned some factors like high-yielding varieties, irrigation, fertilizer, and markets. And there's this important factor that's climate endowments. Quite a lot of researchers point out one of the major constraints in Sub-Saharan Africa is its unfavorable and diverse climate. In the case of Sub-Saharan Africa, as opposed to Asia, unfavorable usually means dry climate. A number of studies show significant effects of climate and crop use, particularly positive effects of rainfall. That means if rainfall is scarce, crops don't grow. Another thing is diverse climate, which results in producing a broad range of staple crops, leading to limited scale benefits of investing in standard technical packages, as in the case of Asia. And of course, there are other factors, such as the underdevelopment of irrigation and insufficient fertilizer use. Because the Asian Green Revolution technology has been recognized as dependent on intensive and controlled supply of water and fertilizers, the adoption of improved technologies in SSA has been confined to limited regions under favorable conditions. However, some recent studies point out there's potential for African agriculture. For example, in India, envies of cereal crops were introduced in favorable areas at the initial stage of the GR, but the envy adoption rate in unfavorable areas started to pick up at a later stage as technology continued to advance. So my objective here, let me rephrase my objective. Conventionally, the Asian Green Revolution technology has been recognized as a resource-demanding technology, which relies on the intensive use of water as well as fertilizers. That means the GR technology generally results in aggravating the adverse effect of harsh climate on crop yields. Conversely, if newer technology adoption leads to a reduction in the agro-climate dependence of crop yields, that would make a positive case for the possibility of an African Green Revolution. Well, there are many say, experiment-level evidences, but no empirical evidence has been found on this. Therefore, it would be interesting and important to empirically explore whether and to what extent the influence of agro-climate conditions on crop productivity has augmented or mitigated by the GR in Asia. Let me just emphasize the contribution of the study. That means what's new in this study. The overtime changes in the impacts of agro-climate on crop yields, which have yet to be unveiled, are examined. Few studies on the subject have ever employed a panel dataset that covers sufficient observations along cross-sectional, temporal, and crop-wise axes due to the date constraints. This study uses a crop-by-crop, district-level panel over a long period, covering 31 years, which has at least 3 advantages over the existing studies. The use of fixed or random effect can control for the unobservable time-invariant district-specific effects, which can mitigate omitted variable problems. And it can also alleviate estimation biases which may arise from, for example, from endogeneity of explanatory variables and sample selection. Number 2, the long-term dataset enables the assessment of the overtime changes in the impacts of climatic conditions. This can be done by pooled data as well, but not by one-point cross-section data. Number 3, yield functions are estimated for each individual crop and are compared with each other, which leads to finding the comparative advantage of one crop over others in certain production environments. Okay. Let's look at some key statistics before going into econometric analysis. Here's a similarity between India and Sub-Saharan Africa. It shows the proportion of area harvested to different major crops in the world. It's cut here. It's sorghum, millet, maize, rice, wheat, and other, in 3 different regions of the world: SSA, India, and Asia, excluding India. The 2 dominant crops in Africa, sorghum and millet, have 47% share, but they are only 2 to 3% in other Asia. India stands in the middle with 21%, which is much closer to the level in Sub-Saharan Africa, which implies a similarity in agro-climate, and that implies transferability of technology from India to Sub-Saharan Africa. And interestingly, if you go back to the early 70s, the same share was 35, which is even bigger to the level in Sub-Saharan Africa today. This column and this column express the same thing, but they're just from different sources. They represent the same thing. By the way, this is pearl millet field in India. Although the cropping patterns are similar between India and Sub-Saharan Africa, the yield is different. It shows the combined cereal yields, 3-year moving averages, in India, Sub-Saharan Africa. Despite the much less favorable conditions in Sub-Saharan Africa in terms of many things: infrastructure, market, education, governance, credit, many things. The yield in Sub-Saharan Africa was not that inferior to that in India up until this early 80s. That means those factors were not decisive. And then it started to diverge. And today, this huge gap of almost 2-fold. Next is the same statistics, but by crop, and separately for India and Sub-Saharan Africa. You still notice rice, wheat, maize, sorghum in India. But when it comes to millet and sorghum, which are the dominant crops in Sub-Saharan Africa, the yield levels are almost the same between India and Sub-Saharan Africa. And since India is the almost only country in Asia that grows millet and sorghum, this means a limited transferability of technology for millet and sorghum from Asia to Sub-Saharan Africa. Okay. These charts, the graphs were summarized into these tables. It shows the average yield in the early 60s and in 2000 for wheat, rice, maize, sorghum, sorghum millet. You notice that wheat yield increased 3.1 times in Sub-Saharan Africa, which is actually comparable to the growth rate in India, which is 3.0. Also, this column indicates India's yield divided by Sub-Saharan Africa's yield. That means India's advantage over Africa for each of these crops. And you may think about technology transfer from India to Sub-Saharan Africa for rice and wheat. And for wheat, yield is growing in Sub-Saharan Africa. Now, is wheat a promising crop in Sub-Saharan Africa? Then you need to think about limitation of wheat expansion in Sub-Saharan Africa. Wheat can be grown well only under a cool climate, which is associated with the temperate climate zone, which is this pink area. In the African continent, the temperate climate zone is found only in limited part, only the northern and southern. And the north part are excluded from Sub-Saharan Africa. So it's only here. As a result, wheat is grown only in the Republic of South Africa, the highlands in Ethiopia, and a few other regions, which is matched with the mere 3% of the total crop area planted to wheat, which we saw earlier. In fact, wheat is not expanding in Africa. Here's how cropping patterns have been evolving in India and Africa. As you see from AGR, average annual growth rate, farmers in India seem to be planting more and more rice, wheat, maize, replacing sorghum and millet. Another thing is the total crop area has been stuck. So production growth has to come from intensification. In Sub-Saharan Africa, all crops except wheat are extending, particularly rice in recent years. So the figure is not showing. But the AAGR for rice is 2.6, and 1.2 for millet, 1.2 for sorghum, 1.5 for maize. Okay. Here are irrigation rate and MBO adoption, only for India. For Sub-Saharan Africa, I don't have the data. What's interesting here is MBO adoption rate increases rapidly for all crops, even for sorghum and millet in recent years. Whereas irrigation rate has been more or less stagnant, but it varies across crops. These C4 crops may not require so much irrigation. And for wheat field, irrigation is almost 90% available. Rice may have some potential. Just a quick look at climate and crop choice. I took the 5-year averages of temperature, rainfall, irrigation, and yield over the district where each crop is grown. You can see wheat growing districts have lower temperature. Wheat is known as a winter crop in India. And obviously, rice growing environments have relatively high rain. And for millet, it's lower. Okay. The most difficult part of this project is database construction. India now has about 600 districts, and the number has been steadily increasing as more and more districts declare independence. And I constructed these variables from these raw data, and those data come from different sources, both public and private. And we actually purchased data sets from CMIE and DataNet India for $3,000 US. It's not me, but my co-author paid for this. Across these variables, the commonly available years are 1972 to 2002. And this is actually exactly the Green Revolution period in India. Here's the econometric model I use. The basic idea is to estimate yield functions by crop. But since each crop is grown in many districts, but not all, I try to eliminate sample selection bias by two-step estimation in the way proposed by Heckman. So in step 1, estimate crop choice function by profit. And the explanatory variables here are normal climate, represented by 3-year moving averages of temperature and rainfall. And also there are square terms. Also included is standard deviation of rain, to see if the volatility of rainfall matters. And this one here is irrigation. It's not crop by crop irrigation, but the district irrigation level. And also literacy rate and population density are included. These two are also included in the outcome equation, the second step. And then inverse yield ratio is calculated using the result of this profit estimation. Then in the second step, we estimate the yield functions by crop. This C here is a vector of climate variables, temperature and rainfall. And then let's just skip it for now. This irrigation coverage rate for each crop. I is for crop. And then X is a vector of district characteristics, population density and literacy rate in this study. And T here is the time trend variable. I include this to account for smooth improvement in technology and the square term. And tau here is a vector of year dummies. I include all year dummies except the base year. And lambda here is the inverse yield ratio calculated from the result of the product estimation. And since this is panel data, we can control for district specific effect. It's mu. And we run Hausman tests to determine whether the fixed effect and random effect to use for each estimation. And the trick here in this specification is the interaction terms between time trend and climate and other explanatory variables in order to examine whether there have been overtime changes in the impact of climate and other variables due to any technological change. Okay, this is just to help you get the picture of the climate effect graphically. Since neither flood nor drought is good for achieving high yield, we usually assume this kind of concave yield function. And then the marginal effect is the slope of the tangency on the yield curve. And on the horizontal axis may be some input like rainfall temperature. So if it's rainfall, maybe Southeast Asia is here and Africa is here. And this slope, marginal effect, may differ from place to place depending on the climate input. And also, if you stay in the same place, the slope can change if the technology changes, if this curve shifts. And the question is, how the curve shifts? Say this is traditional variety. Researchers claim that early generations of MVs are resource demanding and sensitive to harsh agroclimate. That means it's only higher yielding under favorable production environments. But the performance is even poorer than traditional varieties. And then the marginal effect also increases from traditional varieties level. What about newer technologies? If technology further develops from this early MV curve to newer MV curve, then it's more resistant to harsh climate, and the yield is not really bad. And then the marginal effect goes down, it may go down, depending on the type of technology. So that's what we want to look at in this study. Okay. Here's the estimation results for rice. Take rice for example to explain. These circled figures indicate the impact of temperature, rainfall, irrigation coverage, population density on rice yield. And these are found to be all positive. Quantitatively, the interpretation is for a 1 degree rise in temperature, rice yield increases by 11% on average, holding other variables constant. And also, the rainfall elasticity of rice yield is 0.58. Here. And for irrigation, 1 percentage point increase in irrigation rate leads to 3.2% rise in rice yield. And here it's the population density elasticity being 0.09. The last result on population density is supportive of the induced innovation hypothesis proposed by Professor Hayami and Mutan, which states that as population increasing scarcity of land induces the land saving and yield enhancing technologies. Well, it's not a formal proof, but it's supportive of it. Okay, now shift the focus to the interaction trends. These indicate the impact of climate, temperature, and rainfall on rice yield decreases over time because the coefficient on the temperature time trend interaction term is negative as opposed to this coefficient being positive. So it decreases over time at a diminishing rate because the coefficient here on the temperature and temperature time trend squared is being positive. So if it's positive, negative, positive, it means the positive impact decreases over time at a diminishing rate. The same goes for rainfall. The impact of rainfall on rice yield is positive, but it decreases over time at a diminishing rate. Here, for irrigation, it's a bit different. The impact is positive, and it increases over time because the coefficient here is positive. But the rate of increase slows down over time because this coefficient is negative. So that's how you interpret these variables. Another important thing is the the effect of irrigation on climate effects. Since this coefficient are negative, that means irrigation can reduce the dependence of rice yield on climatic factors to some extent. And what's more important here is the overtime changes in the impacts of climate are distinct from the influence of irrigation, since those factors are controlled here. Therefore, the critically important finding is that the dependence of rice yield on climate mitigated over time, regardless of the availability of irrigation, which cannot be understood without considering the impact of the MVs, with shorter maturity and drought tolerance traits. Here are the results for all other crops altogether. These brown circles indicate the declining impacts of climatic conditions on crop yields. And then the green circles indicate the irrigation leads to a reduced climate dependency of crop yields. And also, the orange, this is actually orange. These orange figures show a positive effect of population density, population pressure on cereal crop yields. That supports the induced innovation hypothesis. Even for maize, the effect was originally negative, but actually becomes positive around 1990 or something. And for meal also, population density effect was insignificant at the beginning, but it increases over time. So at least for recent years, the effect of population pressure is all positive for the crops.
Is population trending?
Population, sorry?
Population is trending. Population density is trending over this time.
Yeah, it's been increasing very fast. Okay, I'll give you concluding remarks. First, I summarize the findings and then offer implication based on those findings. Even from the descriptive statistics, there are some interesting findings. Number one, the gap in the aggregate cereal yield between Asia and Sub-Saharan Africa was so minor until the early 1980s, despite the much more favorable climatic, economic, and political and other conditions in India. That means the yield diversion occurred due to the adoption of improved technology in Asia and the failure of that in SSA. In other words, the Asian Green Revolution is likely to be a technology-led revolution. Number two, the Asian Green Revolution technologies were developed principally for wheat and rice, followed by maize. In fact, Indian farmers have been steadily replacing the lower yielding crops, sorghum and millet, by the higher yielding crops, wheat, rice, and maize, which is one of the reasons why the compound cereal yield has been growing in India. Number three, given the absence of the yield difference for sorghum and millet between Asia and Africa, even today, the technology transferability from Asia to SSA for these two crops seems to be absolutely limited. Now I go over the results from the regression. Number one, the impact of climatic conditions, temperature and rainfall on crop yields have reduced over time due to the adoption of MVs and associated technologies. The impact of temperature, whether the average is positive or negative, declined for rice and maize. The rainfall effect mitigated for wheat, rice, and sorghum, which indicates that traits of MVs have contributed to alleviating, not aggravating, the influence of climatic conditions, which is in contrast with the conventional notion that MVs are typically resource demanding and are higher yielding only under favorable environments. Number two, rice MVs require more irrigation water than the TVs, traditional varieties. Interestingly enough, the rate of increase in irrigation effect is relatively large in the initial phase of the GR, but slows down in the later phase. Also, irrigation works to mitigate the influence of climatic endowments on crop yields. Number three is the induced innovation hypothesis proposed by Hayami and Rutan is broadly supported. Continued population pressure is likely to have increased the relative profitability of land-saving and yield-enhancing technologies along the lines of the induced innovation hypothesis. Here are the policy implications based on the findings. It is highly desirable to reverse the declining trend in investment in international agricultural research activities to enhance agricultural productivity in regions with unfavorable climates, including SSA. Number 2 is about crop forecast. Facing a tight budget for international agricultural research, crop-wise foresight would be necessary to clarify policy priorities. For rice, a critically important implication of this study should be a focus on rice as a strategic crop in SSA. Because of the abundant evidences of improved resistance to harsh climate and the large gap in current yield between Asia and Africa, indicating an opportunity to transfer the Asian technology. For rice, since maize is the most widely cultivated crop in SSA, the productivity of maize farming must be enhanced. The advantage of maize crop is that the yield is not adversely affected by the unavailability of irrigation, meaning that maize has comparative advantage in rain-fed farming systems. Therefore, maize can be the second strategic crop after rice. Yet, it must be recognized that unlike rice, maize technology developed in Asia is not conducive to weakening the impact of drought on maize yield. For rice, the limitation of wheat area expansion in SSA requires due attention, in spite of its outstanding yield growth in Sub-Saharan Africa. For sorghum and millet, there exists no difference in yield at all between Asia and Sub-Saharan Africa. Technologies for sorghum and millet in SSA are unlikely to be developed from the experiences in Asia. Number 3 and 4. Try to switch from low performers to high performance, as it has been a driver for achieving growth in overall crop productivity in India. Also in SSA, by the mid-20th century, maize had immigrated and replaced much of sorghum and millet fields in eastern and southern Africa, partly because maize yield more grain. That is, whether TVs or MPs, crop shift from sorghum and millet to rice and maize, wherever applicable, is strongly suggestive of fostering the agricultural productivity growth in Sub-Saharan Africa. Number 4, investment in irrigation can be an effective measure for tackling the harsh agro-climate environments in SSA, as well as the looming threat of climate change. Okay, and this is basically the end of this presentation. But from this study, 2 papers are published in the following book, and 2 other papers are currently under review by economics journals. And there's also another research plan for this year, which is to apply spatial econometrics to the district-level database in India and identify district-level agricultural technology spillover effects for each of the 5 crops at different timings during the green revolution. And this research will be joined by Bob. Thank you very much for listening.
Thank you so much, Taku, for such an interesting presentation. So the floor now is open for questions. Yes. So, Joseph, please.
Joe? Yes, go ahead.
Really interesting stuff. Time, of course, is just a really rough measure of technology adoption.
Yes.
And so how confident, I mean, what else could be changing? What else might be changing over that time period?
Mm-hmm. One thing is that the MD adoption rate variable is not available at the district level. It was only available at the state level. That's one thing. So we decided to go for time trend, for proxy technology adoption. If you look at this the right-hand side panel, for all the crops, the MD adoption rate and time trend are they seem to be highly correlated. So that is one reason we decided to go for time trend. Another benefit of using time trend is time trend variable is absolutely exogenous, as opposed to technology variables that tend to be endogenous.
Some more questions? Yes, please. regarding your heat tolerance, regarding the temperature, you said that increase in temperature will increase in yield in one particular slide. I believe that in the future it will be not so, because the temperature will create a lot of spikelet sterility and pollen sterility and
Temperature effect on rice?
so that will create more of sterility. So beyond the 38 degrees centigrade, you will have a opposite effect of what you're saying.
Yeah, beyond some level of temperature.
Yeah.
Right.
So I believe this is between 1972 to 2002 is only applicable for that period, and in the future it will not be so like that.
You're talking about India?
Yeah, the world in general.
Well, the marginal effect, whether it's positive, negative, or insignificant, it can depend on the input level of the variable. So it may be negative.
No, the temperature will cause the pollen sterility basically. It will have a direct effect on the pollen sterility, and it will cause spikelet sterility. As a result, the yield will go down, not increase, when beyond it goes a particular biological limit of temperature. So it has a limitation at the above level, that beyond a particular level it cannot go what you're saying. Maybe it's true for carbon dioxide.
Yes, I'll give numbers.
That's
Sam number 1, Rod number 2, David 3, and 4. So, Sam.
Maybe to just follow up on what Dr. Ali is saying. Have you calculated a threshold level for temperature rainfall where you see the
threshold?
Yeah. Maybe it will answer his questions in terms of where the effects of temperature rainfall will have negative on both yield. Then my second question is, the Hayami and Rutan's hypothesis on population density induces innovations. Is it possible that population density is capturing, because when the population density increases, you expect the marginal land to go out of production into more human habitation, then the remaining lands are more productive than the land before, then the average yield should have a positive effect on the average yield. So instead of capturing the innovations in innovation, it's for capturing the land quality effect.
It's not a formal evidence of that hypothesis. And then the important assumption here is the marginal product of labor is sufficiently low in this case. But I understand your point.
Okay, number 2.
Yeah. Again, following up on the questions on the temperature effects, I guess this is sort of showing the average impact at the mean temperatures. It would be helpful, I think, from what Sam was saying, is that you have to compute marginal effects at the low, at the high temperatures, because you would expect at the high temperatures, yield effects the effect of temperature on yields will be negative.
Yeah, sure.
And then you have to show that the interaction terms also is decreasing the value of that negative effect. And that's, I think, what the points are here, that you have to compute the marginal effects at different points of the yield function is to be more convincing. So that result will show that, say, the bad temperature at the high temperature, if your hypothesis is true, is that the effect of the bad temperature would be lower as more varieties or more modern varieties, or as time goes by, in this sense.
Yeah.
Right?
It is true that it's the average.
Right. So that's why you're getting that positive effect. So you have to compute it where the temperature effects are negative.
I think that's true for all the three variables.
Yeah, for rainfall as well.
Rainfall and population density, all of them. Eventually, we'll have the marginal effect will be negative.
Right. So you have to show that effects will decrease.
Yeah, actually, in the paper version, I used the quadratic terms for those inputs, and then they show the similar result. But in this presentation, I tried to keep it succinct by excluding the second order term, third order term.
Or you could do, is this log linear, or your temperature is in linears? Because you could do some sort of log thing.
Temperature is not log. because it's an interval scale variable, it cannot take log. It can be negative. If the variable is negative, it cannot take log.
It could be 0.
The yield is log.
Next question is just on the specification. Do you have input use? Because that's another thing, following up on Joe's question, your team might be capturing the input use and all this new pesticides, not just the modern varieties, and that could compound your results. You know that
all those technology factors may be coming in a compound way.
Yeah,
they're highly correlated.
So that's
what the compound effect of all the technical package.
Yeah, so you just have to be careful between in terms of interpreting your T as modern varieties rather than the whole technological change over. That's.
Shall we go to number 3, David?
Oh, okay. Actually, I hadn't raised my hand, but I did want. I might as well use the opportunity. I think we do have to be very, very careful about using time as a proxy for modern varieties. I think it would also make sense to have more disaggregation by the favorability of the production environment, because there are certain. If you did this specifically focusing on rain-fed environments, I think you would find very, very different conclusions. Because I don't think this treatment of irrigation is sufficient really to draw conclusions about stress tolerance.
Actually, in the paper, I did some study using proxy variable. We found high correlation between MV adoption rate and irrigation rate in the early stage of irrigation. Only in the early stage of irrigation. For wheat, it was 0.76, and rice 7.9, maize 52. So for the early stage of grain revolution, for wheat, rice, and maize, MV adoption rate and irrigation rate are highly correlated. So I did some extended study using district level irrigation rate as a proxy for technology adoption rate. And the result was somewhat similar.
Yeah, MV adoption certainly has progressed into more unfavorable environments. But the question is then the effect, whether in the unfavorable environments you see much of a stress tolerance effect yet. I mean, even if you talk with the breeders, they'll say there's some improvement in adaptability. But generally, major innovations in terms of drought tolerance haven't been that widely adopted yet. So we have to be, so it's a bit counterintuitive to have a conclusion that we've had major effects in terms of, say, drought tolerance when the breeders don't even feel that they've had varieties that have high levels of drought tolerance that are that widely adopted in those environments. So that's why I think, even though MV may be present, you still have to really separate out this irrigation effect, the MV performance in rain-fed environments compared with the MV performance in irrigated environments. In order to.
That would be ideal.
So it's actually it's a three-way interaction.
Okay, can we now go to number 4?
Thank you. Because I'm working on temperature, so I will just continue the questions about the temperature because I have a few comments. For the temperature effect on the rice production, I think from Xiaobin-Peng's paper, they have stated that the minimum temperature, the light temperature, the minimum temperature, with 1 degree increase, the rice yield will decrease about 10%. But now we are not clear the maximum temperature, the highest temperature, 1 degree increase, how much the rice yield will affect it. And because your research is mostly focused on temperate region, so the temperature rise, the rice yield will rise. That's right.
Yeah, from the average.
Yeah, but if you focus on the tropical region, the temperature rise, the rice yield may decrease. So this will be
Actually, I found a negative impact in Sub-Saharan Africa.
So maybe you need to identify those hot regions, because now we are working with IRRI to map the high temperature in the India and Africa region. So maybe you can identify those hot areas and to see what difference between the tropical and the temperate regions.
Actually, I know one researcher is showing a negative impact of rainfall on rice productivity. That literature employs a state level analysis.
Okay, I saw sorry. Is it fine? Yeah. Okay. I saw Dr. Castillo's hand. Dr. Castillo?
The transferability of the Asian experience to Sub-Saharan Africa has been a long-term proposition. Before Jack Juve became Director General of FAO, he came here, and when I asked him what his mission was, and he said he wanted to learn from the Asian experience to see if it can be transferred to Africa. After that, Norman Borlaug, through the Tsusaka Foundation, had a big project, the big splash. But after that, there was very little heard about it. Now, I think we are going to succeed, or succeeding more, because of changing socioeconomic circumstances.
In Africa.
The rapid urbanization is creating a demand for rice. So the reverse research approach, starting from the market, seems to be working better than the old concepts. So I don't think it is climate that matters. It is the socio-economic, socio-cultural circumstances which is encouraging this more success. Although there are a lot of bumps along the way, ethnic problems, political problems, but why don't you look at that factor? Because I think that might explain our impending success in Africa. The socio-economic circumstances, urbanization. When people get urbanized, they don't want the discomfort of processing sorghum, millet, cassava, which takes time and energy. While rice, we just put it in a pot, and it's ready to eat.
That's why the demand for rice in Sub-Saharan Africa is increasing. The demand for rice comes from the urban population in Sub-Saharan Africa. It's true.
So make that your next project. That will contribute greatly to Greece. So I think that Norman Borlaug project didn't work out.
Maybe he was ahead of time. There was no demand for rice, so
Yeah,
you know.
there was no demand.
So we know that demand determines supply, not vice versa.
Yes.
I think the readers will disagree with that. But economists, we feel demand is the one that determines the supply.
So make that your next project.
Thank you, Dr. Castillo. I have a question. To follow through the point of Dr. Castillo, I just wonder if you can give us your insights, some cultural insights, particularly on the food and the staple food preference between India and Sub-Saharan Africa, and what is its relation to the likelihood of increasing rice cultivation in Sub-Saharan Africa.
Let's show the statistics today. The most major crop in India is, at the moment, is rice, accounting for 44%. The rice yield is still limited to 10% of crop area in Sub-Saharan Africa. And also, there's a huge diversity in ethnicity and culture in Sub-Saharan Africa, as well as in India.
So,
different regions, in different regions, people have different preference to crop.
So, okay, that's why I asked, just to strengthen the point of Dr. Castillo, that for your next project, it will be the socio-economic and cultural aspects. Yes.
Thank you very much.
Thank you, Taku, for your presentation. Somewhere you mentioned irrigation mitigates the climatic change, and that's why the suggestion from your study that in Sub-Saharan Africa, the rice with irrigation has expanded. Do you think to face the climatic change in Asia, like rice, other crops should be more irrigation? I don't know. What do you think?
Yeah, most of the wheat area is already irrigated. It's almost 90%. Yeah, maize requires a little bit of irrigation that enhances the maize yield. But at the moment, sorghum and millet don't seem to require irrigation. Those crops are a C4 crop that don't demand a lot of water input. They're relatively resistant to drought and insufficient water intake.
Okay, some more questions? Yes, please.
Just one thing. I recently visited Kenya and I found that you mentioned in your paper that only a few regions in South, in SSA countries they produce wheat.
Wheat.
Actually, yeah, Kenya is really expanding wheat production. There are thousands of sectors they are producing wheat now these days. Yeah, I think you can revise this thing.
In highlands, they can grow.
Actually, in the mountain area, and it is completely mechanized. It is reversed than Asia. In Asia, small farmers, manually they do all things. But in Kenya, it is completely mechanized. And it is rain-fed. Rain-fed means, and also because of low use of fertilizer, they keep fallow a land for, after one harvest, they keep fallow land for another time. But it's really extensive and it's increasing, widening the area.
Is this the urban area, like Nairobi?
Nairobi, but while I was going to Nanyuki, the area, we just took many pictures of those irrigated.
You mean wheat?
Wheat field, yeah. Yeah. In Kenya, it's increasing.
Wheat or maize? I haven't seen
Wheat.
wheat yet. Wheat.
It's actually wheat on the way to Nairobi.
I saw lots of maize there.
And it's completely mechanized. That is the most important part.
Mechanized, you mean it's not done by peasants? Small scale farm?
Yeah, some rich guy in urban area, they're just using this land. And they are mountain.
Okay, thank you.
Some more questions? If there's none, I would like to thank you all for coming, and everyone is invited to partake the food that we prepared outside. So please join me in thanking Dr. Takuji Tsusaka.
Thank you very much.